welcome you triple legends to your latest topic on your triple physics. This is, not going to lie to you, this is probably my favorite topic. And fair warning, next week, second lesson of this topic, I'm going to teach you the coolest fact in science. That's just the way it is. You will learn the coolest, most life-affirming bit of information you will ever hear live, well, I say live, on your triple lesson. But space has always been one of those bits of science I'm just really, really into. I just love exploring space, learning about what's out there. Just the size of it all freaks me out a little bit. So I love this topic. This is the first of the paper 2 topics. We've finished all the paper 1 content. So all those topics we've been doing in triple, electrostatics, your nuclear physics, your energy transfer, the stuff about pressure and gases, that's all your paper 1 content done and dusted. And this is the first of the paper 2 topics. And only you triple folk get to do the space science. So really, I think that's why triple physics is one of the best sort of options. Anyway, enough about how cool I think this is. I want to get this topic started here. And I'm going to start sharing my screen so you can get a title ready there. So I'm just going to get my screen up and going here. And oh, that should do me. So there you go. Here we are. The first part of this space topic we want to look at is the solar system. And I think it's one of those things that we feel we've learned a bit about at Key Stage 3 or even in junior school, or even if you're just sort of watching any sort of sciencey stuff, all the Brian Cox stuff, you know, I love to watch on TV. I think a lot of us feel like we know the solar system. It's like, well, it's the sun and the planets. But for our triple physics, for our GCSE, we sort of need to take that to the next level. We need to have a much more comprehensive view of all the stuff that's in the solar system. And to start off with, we need to think about how the solar system was formed in the first place. So first thing I need to talk to you about is that formation of the solar system. And just to be clear, the solar system is basically everything that feels the gravity of our sun, that star in the center of our solar system. If you are being held in orbit or pulled around by the gravity of the sun, and you're in that area of influence in its gravitational field, you're in the solar system. So let's have a look first of all about how it formed. And if I get my little link up here, there we go. And really, we need to start our story of the solar system formation with just a big old cloud of dust and gas. This is going to play on a loop here. That big old cloud of dust and gas is what we call a nebula. Those clouds of dust and gas were present in the universe. But if those clouds of dust and gas got large enough, or maybe they got a bit of a nudge, maybe from a nearby star getting a bit close, or maybe from a star a long way away exploding, if those clouds of dust and gas, that nebula, felt a bit of a nudge, then something would start happening. It would start being pulled towards the center of that big cloud of dust and gas. Its own gravity would start pulling all that dust and gas towards the center of it. And that would mean you ended up with a big pile of dust and gas in the center of that nebula. And that blob of dust and gas, as more and more gas got pulled into the center of the nebula, you end up with this one blob of gas in the center of that nebula, which is going to become a star. Now, if enough gas gets pulled in, then the pressure and the temperature start building up inside that blob, and eventually that star gets high enough temperature and pressure for nuclear fusion to start, and that's really when it becomes a star. If nuclear fusions start, then bam, it starts releasing heat, light, energy, loads of other forms of radiation, and the energy from that is enough to blow away and evaporate lots of the low melting point, low boiling point, less dense materials that were sitting around near that blob, which has become a star. So you end up with the heavier, more dense materials left orbiting around near that star, but the lighter, less dense, lower boiling and melting point materials ending up being blasted or pushed far away from the star by the energy and radiation that's coming from it. And that's why we end up with a solar system, which is made of the star, our sun, in the center, with objects orbiting near it, which are made of dense materials, rocks, metals, objects with high melting and boiling points. But the objects which are further away tend to have a lot more less dense materials on them. So things like methane gas, hydrogen gas, things which are easier to evaporate or boil or are less dense. So the objects further away from the sun tend to be made of more volatile, less dense materials. The objects nearer the sun tend to be made of more dense, high melting and boiling point materials. So the story you need to tell is this idea about a nebula, a big cloud of dust and gas that gets pulled inwards by its own gravity, forming a large blob of gas at the center of it. Now, if the temperature and pressure get high enough inside that blob of dust and gas, boom, fusion starts. We've got ourselves a star. The heat and the radiation and the energy coming from that star push outwards and cause the less dense, easy to evaporate materials to evaporate and be pushed far away from the star and leave behind the more dense materials still orbiting around nearer the star. And we end up with our solar system. Rocky, denser objects nearer the sun, more gas, less dense objects further away from the sun, and we end up with our solar system. And you're like, yep, absolutely nailed it, sir. There's our sun. We've got our rocky planets, Mercury, Venus, Earth, and Mars near the sun. We've got leftover rocky bits which didn't quite make it into forming a planet. And then we've got our big gas planets further away from the sun, Jupiter, Saturn, Uranus, and Neptune further away from the sun. And that may well be the extent of what you think of in the solar system, but even just looking at that diagram, you can see there are far more objects orbiting around the sun, feeling the sun's gravitational field than just the planets. And you need to have a bit more of an in-depth knowledge about what those objects are. Now, the task that goes with this lesson is this solar system presentation, where you're going to be asked to fill in information about all the objects which form part of our solar system. So I'll go through this information now, and then your task at the end of the lesson is to fill in this presentation and submit it. So let's have a slightly more detailed look at what's in the solar system. This is a live simulation which NASA put online. I'll post the link to it in with this lesson, and you can see it is live. What are we, 28 minutes past 11 on the 29th of January as I'm recording this, and this is a live simulation of everything that's in the solar system, all those objects there in the solar system. So I've got a nice little animation that I can manipulate there and see everything that's in the solar system. So we can see some of the stuff we'd expect there. If I zoom in to the inner solar system, I've got the sun, I've got Mercury, the nearest planet to the sun. Then moving outwards, I've got Venus, then I've got Earth, and then the last of the rocky planets is I've got Mars there. So we've got our three rocky planets nearest to the sun there. One thing I do want to point out about this simulation is that it is not to scale in terms of the sizes of the objects. If I click on the sun and just sort of try and compare the size, if we look at the size of the sun compared to the Earth, that tiny little dot there, the radius of the sun is just under 700,000 kilometers. That's its radius. The radius of the Earth, for comparison, is just over 6,000 kilometers. So the radius of the sun is over 1,000 times greater than the radius of the Earth. The sun is a massive object. 99.8% of the mass of everything that's in the solar system, if I could bundle up everything that's in the solar system, so everything in all this simulation, then 99.8% of the mass of it would be the sun. So the sun makes up a big old chunk of our solar system, almost all of it, and the leftover stuff are just little bits orbiting it. So we've got our inner planets there, which are made of rocky and metallic materials. If we zoom out of this outwards to the solar system there you go, we can see the gas planets which orbit further away from the sun there. So we've got Jupiter, the largest of all the planets in our solar system, more than twice as big as all the other planets combined. If you could roll all the other planets together, Jupiter still has about twice the mass of all the other planets combined together. Then Saturn, with its beautiful ring system, made mostly of frozen ice materials. We've got Uranus, which is special, A, because it's got a funny name, B, probably because of some massive impact that hit the planet a long time ago. It actually is lying on its side. It rotates at an almost 90-degree angle to the orbit that it's on, so it looks like it's spinning almost on its side there. And then finally, the last of the big gas planets, the last planet in our solar system is Neptune, 8th planet, the most distant planet orbiting the sun there, and it's got winds which I think run it routinely over 400 miles an hour on that gas planet there. So those are the sort of planets of the solar system that we think of, but you can see, even just looking at this simulation, that there are loads more objects in there. First thing I want to look at is just to point out that if I lie the solar system on its side, so that's a top-down view, but if I lie it on its side, you can see that almost all those things that we've just been talking about there, all those planets, lie pretty much on one big flat plane. I could almost put the solar system on a table and all the planets would be level with each other. But there are other objects orbiting at a bit of an angle, not flat. That's a good clue that they probably weren't part of that original series of planetary formation from that nebula. So they maybe formed at different times or got knocked out of orbits, but they are orbiting at a very different angle to the other planets. And some of those, probably the one you've definitely heard of is Pluto. We used to count that as a planet. We now count that along with these other objects, which don't orbit in the same plane, don't have the same mass, don't have the same characteristics as the other planets. We count them as dwarf planets. So you've got Haumea out there beyond the orbit of Neptune. We've got Makemake also out there further away from the sun. And we've got dwarf planets in the inner solar system as well. If I can zoom in and find it. Oh, I think I just went off the side of my screen there. Oh, there's Ceres there. So there's Ceres, which is a dwarf planet in the asteroid belt between Mars and Jupiter. So we do have these smaller objects orbiting the sun, which we don't class as planets, but we classify as dwarf planets. So that's the next object we need to think about when we're talking about the objects in the solar system. We've got the sun, we've got the planets, we've got the dwarf planets as well. There are smaller rocky objects as well. Perhaps most famously here in the asteroid belt, we've got these asteroids, these rocky, dense objects orbiting around the sun. Eros, classic example there, and we have one which has been in the news recently called Bennu, which is an asteroid about the size, it says on the screen there, as the Empire State Building in New York. So we're talking significantly smaller than the planets and the dwarf planets. Whizzes by, has an orbit of about 1.2 years, and every now and then gets closer to Earth than some of the other asteroids we may have heard of. So we've got planets, we've got dwarf planets, we've got asteroids, and then flying around at an even weirder angle. Oh, see if I can find one down here. I'll zoom out of my solar system. We've got other objects. There you go, the comets. Probably the most famous one is Halley's Comet, and these are on big, wide orbits of the sun. Halley's Comet has an orbit which brings it back to Earth about every 75 years or so. It was last orbiting around Earth in 1986, so you can do your sums and figure out if you're likely to see Halley's Comet again. And these comets are objects made of leftover dust and ice from the early formation of the solar system, which orbit around the sun on these very strange orbits, sometimes getting very close to the sun, sometimes getting far away from the sun. And as they get close to the sun, those icy materials start evaporating off them. So we see comets with lovely streaky long tails, if we can see them in the sky. And there are other comets, but I can't see them on my screen. Oh, there's Tempel 1. There it is there. There's Tempel 1, which is another comet as well there, which we've actually managed to send robotic spacecraft to examine it. So planets, dwarf planets, we've got asteroids, we've got comets, and we mustn't forget the other objects in the solar system, which are the moons. Now, the moons are the solid bodies, or the bodies which orbit the other bodies in the solar system. So you could have moons of Saturn. Saturn has over 62 little moons orbiting around it. Mars has 2 small moons orbiting around it. Even some of the dwarf planets have planets, I beg your pardon, have moons orbiting around them. If we look at Haumea, we know it has 2 small moons orbiting around Haumea, and I'm not going to try and pronounce them. I believe it's Hilaka and Namaka are the 2 moons orbiting around Haumea. So these are natural objects orbiting around other bodies in the solar system, and those are the moons. So it's not just as simple as talking about the sun and the planets going around it as being in our solar system. Our solar system consists of all the objects within the sun's gravitational field. So you know your job now. I've given you that quick overview. It's your job now to go in and fill in the details in that presentation attached to the lesson about all the different objects in the solar system. It's going to ask you to provide some details about the different objects in the solar system, as well as the formation of the solar system. And once you've finished that presentation, submit that back to me. Just like last time I gave you one of these research presentations, I've turned the plagiarism filter on, so I'll be able to see if you're just cutting and pasting from places. I'd rather you give me small amounts of information in your own words than a copy and paste off nasa.gov or Wikipedia or whatever. I need to know what you've learned about those different parts of the solar system. That is it. Don't forget, next week is the coolest fact in science, bar none. I'm telling you now, I'm not lying to you. This is genuinely the most life-affirming, fabulous fact you will ever learn in science, and it's happening next week in your triple physics lesson. Please drop me a message, give me a shout if you've got any questions, or you find anything you want to tell me about the solar system, and otherwise I'll catch up with you next time, guys. All the best.